Hi everyone, we're almost ready to get into tuning, but before we get into tuning we need to understand the controller. We just got done talking about the process. The process is essential. You have to identify the characteristics of the process gains, time constants, type of process. That's important. Whether you walk and look at it or do a bump test or do a Newton's laws of physics, you have to calculate or determine what you're working with. Then we go into the controller. We have to understand, well, what is this thing? What's a proportional? What's an integral? What's a derivative? What are they? How do they work together? This particular series of discussions has been one of the most complicated series to try to capture because there's a lot of material to cover here. So you may need to watch this a couple times or go in the book where it's all written out. Now, what we're going to talk about here is feedback controllers. Your feedback controllers, like if you're driving down the car and you're looking in the rear view mirror and you're trying to make adjustments based on what's behind you. Although that seems odd, you would never do that, or if you're going to do that, let me know so I can get off the road. Feedback controllers do that. The error has to happen first, then the correction starts. That's kind of an important distinction on controllers, as opposed to feed forward. Feed forward is like you're looking out the road and you see a pothole and you adjust for it before the error happens. Feedback control, you had to hit the pothole and then you're always late. So keep that in mind, is feedback controllers, proportional, integral, and derivative, are reactive in nature, and that is what defines the control actions and the way you tune them. 90% or more, 95% of all industrial controllers fall into this PID algorithm. Yet it's one of the most misunderstood areas that we have. If you look at the history of where controllers came from, the different industries, there's a lot of different forms of the PID, there's a lot of different tuning parameters, there's different units, and quite frankly, you could be very good at one controller or manufacturer and then change to another one, put the same numbers in, and blow something up. So it has given tuning and controller kind of a bad name. It's like, well, it's a black art. It's magic. You're just throwing numbers in until you get it to work because there's no rhyme or reason to it. For someone that hasn't been taught the differences, it does look like black magic. That's why this particular section is really important. It's important that you understand what a controller is, what its function is. It'll help you in your troubleshooting. It'll help you with time to commission a project. It'll help you when you're flipping between different vendors. Most industrial plants have a whole range of controllers, types, processes, manufacturers. So you can't just lock yourself into one type of controller. So that's what we're going to cover here today. This series, we're calling it Feedback Controller, is really broken up into the attributes of the error. We're going to start there. What is an error? And then answer that. Then we're going to get into what is proportional, integral, and derivative. Those are mathematical terms. And as soon as we talk about math, a lot of people go, oh, I don't know math. Well, we're going to try to boil that down and show you how that works. Then we get into the interactions. You very rarely will use proportional by itself, integral by itself, or they actually interact. But if you don't know how they work individually, you'll never know how they work together. Then it gets real fun is when we get into the forms of the PID algorithm. That's where different manufacturers have different forms, and we'll talk about those. And then I'll wrap up with just some considerations when you're selecting a form or using a form on different filters, different things. We'll wrap up on that. So here we go. When we look at this, we have a trend. This is a trend showing the set point or the reference, and this is the process variable, the measurement. And those circles represent, the execution. In today's digital world, it's not analog where you have a continuous stream of data. You have a sample. So we have these sample points. So something that was really good here, and then all of a sudden something happened. And so what we have is an error. And the error is defined as the set point minus the process variable. Now, if we were in a classroom setting, I would say, tell me, what are 3 things that you could see or define in this trend? Something happened, yes. I mean, don't say, well, pump number 5 upstream shut down. No, it's just 2 lines on a sheet of paper here. What are the characteristics or attributes that you might come up with? So just think for a second. Just, what are 3 things that represent what you're seeing here? And now we're going to go ahead and answer those. There's really 3 things that falls into. If you look at it, there was a magnitude of change. There was something happened, and I had a magnitude, the difference. There's an error. So there's a magnitude of error. Then we notice that the error didn't go away. There's a duration. You notice that there's an area or an area under the curve or a duration of the error. And then the last one most people have a hard time seeing is the rate of change. You know, it's really the slope. You know, how much did this slope change based upon the difference between 2 points? So those are really the three attributes that define what we're looking at here, is the magnitude of the error, and it really defines the present error, the now error, what's going on right now. Then we have the duration of the error, which gives us an insight into the history or past error. And then rate of change is a indicator of the future. Where's this error going? You know, it's a rate of change. So those are the three numbers that or three attributes of any measurement or control system. That's important, and we're going to play off of that throughout the remainder of this talk. If you notice, there's proportional, integral, and derivative. There's three parameters in a controller. What do those line up with? Well, right here. Proportional control is designed to work with the magnitude of the error. Integral control is designed to deal with the past error, or the area under the curve. And the derivative is designed to deal with the future error, or the rate of change. So in mathematical terms, proportional is like a teeter-totter. If it goes, you know, it's literally just like a teeter-totter. Integral is it's looking at the area under the curve and translating that into an output. And derivative is looking at how fast this change occurs and trying to adjust the output based upon that. That's what we're going to keep coming back to, is if you can boil back down to the very, very fundamentals. Proportional deals with the present error. Integral is like a watchdog for past or the duration. And derivative deals with the future, or predicting the future. Mathematically, this is where about the extent of the math we're going to get, is the U represents the output of our controller. So the proportional component is simply a tuning, is a p-value, usually it's a gain, it's a multiplier, times the error. So this is our current error. So you can see if my error dropped, then I would make an output that was proportional to the error. They look the same, they're just scaled a little different. We're going to talk about that a little bit more as we go on. This little funny looking symbol here is called an integral. It's a calculus term. We don't need to know what calculus is. It's an integral, which is the area under the curve. So this is saying some I term, a multiplier, times the area under the curve. So what you can see here is as time goes and the area goes, the output for integral grows with the duration. Okay? This one is what the derivative is. D is the delta, or the change in error over the change in time. It's a slope calculation. And D is a multiplier for the slope. So here you can see the slope is 0. Here you see the slope is 0. But here the slope was equal to that rate of change. So it would go along 0, boom, boom, and come back. We're going to spend a lot more time talking about each one of these concepts. But I want to introduce to you proportional. It's a mathematical term. Integral and derivative, they're all mathematical terms, and they apply to that particular error. The job of our controller is to take an input, which happens to be the error, which is the difference between a set point and measured value, and convert it into an action. So here you see my error is the difference between the set point and measured value, and it converts it into an action. That action is a function of the error, and it's a function of the tuning parameters P, I, and D, and that's it. And that action goes to an actuator, and the goal of this controller is to adjust the actuation device to reduce the error, or eventually make it 0, if that's the design criteria. So we're going to start and end on this slide. A controller will convert an error into an action. The action is defined by the attributes of the error and the tuning parameters. And the tuning parameters are a function of the controller type and your preference for how you want this thing to respond when you put it in automatic mode. That's the attributes of an error. We always kind of come back to that as, well, what's going on with this? And now the rest of this is like a big pyramid. We just picked the top. Now we're going to go down and say, okay, go over that proportional, integral, derivative thing again. That's what we're, the teeter-totter, the fulcrum. We're going to talk about that next.